So the next thing that we can calculate is the voltage drop. Each resistor is going to pull some power out of the system, which is going to result in a loss of energy or a voltage drop at or after each resistor. And the way we calculate that is still using Ohm's law, but now we're using the resistor value of each individual resistor times the current passing through that resistor. So at this point, we now have a resistance value of 100 ohms, a current of 20.8, and we're looking for a voltage drop across resistor 1. When you see voltage source, Vs, that's the voltage source for the current, for the circuit. If you see VR and then a number, 1, 2, 3, it's saying the voltage drop across this specific resistor. So when you're thinking about voltage drop, the only thing I want you to focus on is these two numbers. So we have a current value, we have a resistor value, and we're looking for a voltage. We're still using the same Ohm's law calculation. So we'll bring this over here. In this case, we're now looking for voltage, which is going to be the current times the resistance. So if we do voltage drop across R1, right here, is going to be equal to the current, in this case total, because the current is the same all the way through the circuit, this right here, times the resistance value of that resistor. So in this case, we're going to be looking at R1. Still the same calculation, still voltage equals current times resistance, but we're only looking at the voltage drop across that resistor. So if we plug the values in here, IT, we solved for 20.8 milliamps. And I'm going to write it back in its decimal form, times the resistance value of 100 ohms. Therefore, the voltage drop across R1 is going to be 2.08 volts. So what's happening is I lost 2.8 volts from this 24 volt source across that resistor. That means now if I were to measure with my meter from the reference point here to after this resistor, it would no longer read 24 volts, but it would read 24 minus 2.08, or somewhere in the ballpark of about 22 volts. Now if we continue and do that for all of the resistors, so this was for R1, there's your voltage drop. So the voltage drop across resistor 1 is the total current times the resistor value. We could do the same thing for resistor 2. So let's say that we do the voltage drop across R2. That is again going to be equal to the total current times the resistor value of the second resistor. In this case, this is 150. So if we plug it in, we get IT still 20.8 milliamps, now multiplied by 150. We get 3.21 volts. Voltage drop across the second resistor is 3.12 volts. So that's the voltage drop here. R1, we saw for there, voltage drop here would be 2.08, and the voltage drop across R2 is going to be 3.12 volts. Drawing's getting a little cluttered again. And we can continue doing that for all the values. The total resistance is still the same, so we're just multiplying total current, total current times the resistor of each value, the value of each resistor. This one happens to be the same. It's 100 ohms. That was 100 ohms too. So the voltage drop across R3, we already know it's going to be 2.08. Now with 300, you could do the math on it. The total current, 20.8 milliamps times 300, or also known as 3 times this value right here. So you could say the voltage drop across R4 is going to be something around 6.24 volts. And then for 500, we do voltage drop across 5 total current times the resistance value of R5, which is 500, and the 0.028, 208. Which would be 10.4 volts. So the voltage drop across the 5th resistor in this series is going to be 10.4 volts. Now another thing, the Kirchhoff's voltage law says that the sum of all of the voltage, now remember these are voltage drops, so they're basically lessening, would all equal 0. So if we add all these together, 2.08, 3.12, 2.08, 6.24, and 10.4, we would get 24 volts, meaning the voltage source will be equal to the sum of the voltage drops. And that is true for a series circuit. So if we do 2.08 plus 3.12 plus 2.08 plus 6.24 plus 10.4, and we come up with, and this is rounded off, but 23.92, which basically was the 24 volt source. So Kirchhoff's voltage law says that all of the sum of the voltage drops will be equal to the voltage source. So you can use this later on where we could determine what the voltage drop would be if we knew most of these values and the voltage source. So in this case, we calculated the total current by finding the total resistance, creating an equal current value or equal circuit, and then solved for the total current just using Ohm's law. So a voltage source, a total resistance, and we solved for the total current in this case, 20.08 milliamps. We also know that the current will be equal at all points. I can't, if I've got one path, I can't put more energy in than I'm going to get out. So the amount of current flowing through has got to be equal going in and equal going out because there's only one path. Think of like a garden hose. If I'm putting water in one end, I can't get more or less water out of the other end. It's got to be equal. So the current will be equal at all points. I know this value is true at any point in the circuit. Once I have that, if I'm looking at a specific resistor, I can calculate the voltage drop across a specific resistor by multiplying that total current times the resistance value. Still Ohm's law, I'm just using it in voltage drop time equals total current times the resistance value of that single resistor. All right, I hope that helped in the explanation of understanding the relationship of Ohm's law, voltage, current, and resistance, and understanding what voltage drop was. I'm going to pause the video here. I'm going to start another one, and we can do the power equation for the amount of wattage for each resistor.